All right. Now we are down to our last part actually. The last two parts are being combined here. So, why? Because supposedly the discussion is first focused on the hypothesis testing on single or on one sample. Okay, single sample or single group. Okay, and then the other one is for two samples or two groups. Right? But my slide is somewhat mixed, right? I just did a more straightforward flow, right? Okay, so this is the last but the longest video that we have for this module. Okay, so without further ado, let's start by defining first what is a hypothesis. Okay, so as said here, it is a testable statement, meaning it's a statement that we can prove or disprove. Okay, or maybe it's a prediction that we can prove or disprove. Statement or prediction that proposes a relationship or explanation between variables. So relationship whether one variable is correlated to another or proportional to the other, or maybe whether one variable causes something to change in another variable. Okay, so meaning there's a causation. So in short, we are testing our um, statement or prediction that proposes a correlation or a causation. Okay, so that's hypothesis. So in this module, we are focused more on the causation part. Okay, on explanation between variables. Okay, whether one variable is associated with the other. Okay. At the same time, hypothesis is also one that represents educated guesses formulated to guide an investigation or experiment about the expected outcome based on existing knowledge or theories. So I already mentioned in the very beginning of this module that we do this to usually as part of our scientific method, right? To answer a certain question. At the same time, it could be also part of our engineering design process where we test our solution. Okay? So we can use it to validate our solution also. Okay? Now there are two types of hypothesis. Um, we have the null and the alternative. For the entire course, please take note that the null hypothesis is represented by H0. Okay, or HO na lang for convenience. Okay, the null hypothesis represents the assumption or claim that there is no significant difference. Just remember that phrase, null hypothesis, no significant difference. Okay, or maybe no significant relationship or effect in the population. Okay, for example, there is no significant difference in the mean scores between Group A and Group B. So those two groups. So we are saying that they are just the same. Okay, so it doesn't matter which group you are part of. The scores are the same. Okay, there's no significant difference. They are somewhat at level on with each other. Right? On the other hand, the alternative hypothesis is basically the opposite of the null. So we represent that by the symbol HA. Okay, this one contradicts the null hypothesis and represents what we suspect to be true. It states that there is a significant difference, relationship, or effect in the population. So it's like the reverse, the opposite of null. For example, we are normally when we are our alternative hypothesis normally have this phrase. There is a significant difference in the mean scores between two groups. Okay, so no difference, no significant difference, null. There is a significant difference, alternative. Okay, now We do the hypothesis testing, which is the statistical procedure used to make inferences or draw conclusions about a population based on sample data. And it involves formulating the null and the alternative hypothesis and conducting statistical tests. Okay, so before you can conduct the test, be be clear first. What is your hypothesis anyway? Right? So to do that, to come up with a hypothesis, first we have to identify the variables. We have to clearly define which one is the independent or the factor being manipulated or changed, and which one is the dependent, the outcome being measured. Okay? Once we have that, we state the relationship. We clearly articulate the expected relationship or effect between the variables. So this could be, like what I said earlier, this could be a causation relationship or a cause and effect relationship, or maybe a correlation. So, so we have to state that. What are we doing? Are we testing it to check whether there is a causation between the two variables, or is there a correlation between the two variables? Okay. We specify the directionality. If applicable, specify the expected direction of the relationship, especially if we are conducting a correlation test. We are trying to measure the certain relationship between two variables. For example, does increasing one variable result in an increase or decrease in the other? So that's correlation test. Okay, we want to answer that question. Okay, of course, once you have your hypothesis, make sure that it is testable. Ensure that the hypothesis is testable through empirical observation or experimentation. There should be a way to gather evidence that either supports or refutes the hypothesis. So you have to design your experiment. You have to check, find out how can you perform that experiment in as accurate possible that you can, in the most accurate possible, in the most accurate way that you can. Okay? So that's what we do when we conduct the hypothesis testing. We create the hypothesis first. And then here's a quick guide on how do we choose a statistical test given our null and alternative hypothesis. Right? So the null hypothesis normally says since there is no significant difference, then the mean of the two groups are the same. Okay? While in the alternative hypothesis, since we are saying that there is a significant difference, then we can say that the mean of one is not the same or not equal with the mean of the other. Okay, so that's why you see here HO is equal, HA is not equal. So it goes with the other types of tests as well. Okay, in our case, we are focusing only on up to two samples. Okay, because the third, more than two samples would require us a higher type of test. Okay, although we're going to have a quick look about uh, ANOVA in module 4. Okay, so here we're going to introduce only, right? So now, as you can see, if we have one sample, then one of our here are our options. Okay. So if we have our data is continuous and it meets normality assumption. So by the way, our focus for the course is in this portion, upper half only. Okay. So you can observe the lower half if you want. Um, so we focus here on the upper half only. So again, if our data is continuous and we are assuming it is normal, then regarding the mean, this is our alternative, null and alternative hypothesis. So we can use one sample test for one sample only, or a two sample t-test, whether independent or dependent, um, if we have two samples. But if we have more than two samples, then we cannot use t-test anymore. We can use some other types of statistical tests like analysis of variance or ANOVA. Okay, but basically, if we have one sample, we are just uh, comparing our mean to a known mean, okay, or an accepted mean, okay, like our target value, target um, um, measurement. Okay. So if we have two samples, we are comparing the two, the group A and group B, team A and team B. We are comparing their means. But if we have more than two samples, then that becomes more complicated as there are several ways to conduct ANOVA and other statistical tests. Okay. But normally the HO is still the same. We are assuming they are all equal. Okay, while the alternative hypothesis is one of them, at least one of them is different. Okay, regardless of, let's say we have five groups being compared, four of which have equal mean, but only one does not have the same or very close mean. So that's still not counted as that still supports our HA. Okay. So anyway, again, if our data is continuous and we are assuming it is our distribution is normal, then here are our options if the mean is known. Okay. But if the population is known, then here are some uh options. But remember, chi-square can only be used when we are using categorical data. Okay, so actually the green ones, you can ignore that. We focus on the red ones only. Okay, so to be more specific, let's talk about them. All right, partially. Okay, so confidence intervals, we just take a range of values within which the true parameter is likely to fall with a certain level of confidence. So that's the simplest way for us, or the simplest statistical test that we can do. Okay. But normally we use t-test, z-test, ANOVA, or regression and chi-square. T-test, statistical test used to determine if there is a significant difference between the means of two groups, or maybe just the mean of the measured and the mean of the accepted or the ideal value. Okay, that's actually the same with z-test, but again, the difference is the in terms of sample size. Okay. ANOVA, statistical technique for comparing the means of two or more groups, like what I mentioned. And now we have the regression, so statistical method for modeling and examining the relationship between a dependent and one or more independent variables. So we're going to talk about this in module 4. I mean module 3. Okay, the next one. And lastly, we have the chi-square. So statistical tests used to determine whether there is a significant association between the two categorical variables. For example, if there's an association between the gender of the respondents and um, their favorite color. Okay, so that's an example of to answer that, then we can use of chi-square. Okay, we can ask um their favorite color of respondents from the two genders, or two or more genders. Okay, so we can compare them and then see if there's a significant difference or not. Okay, so this is just a summary, quick overview of what's next. So you can take a screenshot if you want. Okay, so we'll try to take a look more about t-test and z-test, and then a brief of ANOVA and chi-square. Okay, so but first, you have to understand the terms significance level and p-value. So when we say significance level, we are referring to a predetermined threshold that determines the evidence level required to reject the null hypothesis. So somewhat like we are saying, um, we out of all the possible outcomes, we are excluding this portion, um, so that um, we are saying that what our claim is true the, except if it falls within this rejected portion. Okay, so we have such thing as rejection region. Um, Significance level, we use that to reject the null hypothesis, or that's one of our indicators on whether to reject or accept the null hypothesis. Okay. But another way to do that is to derive the p-value or the probability value that measures the strength of evidence against the null hypothesis. So for example, if your uh, statistic, statistic value falls in this certain portion, okay? I hope you can see my cursor. Okay. And our significance level says that we exclude this portion, this last left tail. This is what we call a left tail. Okay, so this portion exclude this, and the portion on the right tail is also excluded. So meaning if this is what we include from -3 deviations, standard deviations up to +3 signif standard deviations, then we are actually considering 6 deviations only. And that is the principle of Six Sigma. So we accept only up to 6 deviations. So the rest, if it's more than beyond -3 deviations or beyond +3 deviations, then we can reject that. If our test score or test statistic falls outside that region, then we can reject the null hypothesis. Okay, so but another way to say that is take note that if this is our limit, somewhat like our limit, if this is our left tail rejection region, then we have this limit. In calculus, actually, this portion can represent a strip of an area. So it's like a slice of the entire region. So this slice represents an area. And normally, as you can see, the higher the height, the bigger the area of that strip. Okay? So that means if our p-value is less than our significance level, for example, this significance level corresponds to 0.1%, then, okay, so we reject the null hypothesis less than or equal. So if it's zero, if this is the 0.1, and let's say you computed your p-value and you have your um p-value as 0.009. Okay, so that's less than 0.01 or 1%. Then that means it is somewhere lower on the lower side because it's lower than the p-value. The p-value is somewhat like the height, okay, or proportional to the height of this curve. Okay, so if this is the height of your limit, which we call the critical value, okay, that's another term. Um, okay, if this is 0.01, I mean 1%, that's 0.001. Okay, and the p-value says it's 0.0009, then 0.009, three zeros, 0.0009 is smaller than 0.001. That means it's on the lower side. Okay. Uh, Meaning, if it's in the lower side, that means it's in the rejection region or the critical region. Okay? And if our computed statistic falls on that, that would mean we reject the null hypothesis. Okay? It's outside the range, outside the limits. Okay? And if our therefore we can conclude that if our p-value is lower than the negative or the left p-value, then or p-value in general, if it's lower or equal than the significant, sorry. If our p-value is less than or equal to the alpha or the significance level, then no further ado, reject the null hypothesis because it falls on the critical region outside of the or accepted region. Okay? So, by the way, the p-value is probability that measures the strength of evidence against the null hypothesis. So against. So we reject if it's below the p-value, the significance value. Right. So here's a summary. What you can forget what I said. You can just memorize this part if you want. Confidence level. So we use our confidence level is just one minus the significance level. So if your confidence level is 90%, then that's 0.9. So if we do the math, 1 minus 0.9, our significance level is 0.1 or 10%. Okay? If we are conducting a one-tailed test, then we reject the null hypothesis if our p-value is less than 0.05. Okay? But if we are doing a two-tailed test, then we reject the null hypothesis if our p-value, the one that we compute, is less than or equal 0.10. Okay, two-tailed 0.10, one-tailed 0.05. But in most professional researches, the one that is usually being used is the 95% confidence level. Okay, so that would mean we are using zero point zero 0.05 alpha or significance level. Okay, and normally between the one-tailed and two-tailed test, the more common is the two-tailed because if we are saying equal or unequal, if our hypothesis says equal while the alternative hypothesis says unequal, then that is actually a two-tailed test. Okay, so if instead of equal and unequal, our hypothesis mentions less than or greater than, so that is actually a one-tailed test. So what is a tail? Again, these are our tails. So we have this left tail and we have this right tail. Right, so let's see the next slide. I believe we have an illustration to that. All right, yes. So we have such terms as acceptance region and rejection or the critical region. Okay, acceptance region is the one that refers to the range of values for the test statistic that leads to the acceptance of the null hypothesis. So, for example, in this portion, in this distribution, we have the critical values as our limits. Okay, so we have the lower critical value, the negative critical value, and the positive critical value. Okay, in this case, we are using the Z distribution. Um, but the principle is also the same with T, F, or whatever statistical test. Okay, so if it falls within or between these two critical values, meaning it does not fall within the blue areas, so it's just somewhere in between, then we accept the null hypothesis, or technically, we fail to reject the null hypothesis, right? So we fail to reject if it falls within this area because it has a higher probability value than our significance level. Our significance level has this much only. But if it's somewhere in between, it has a higher probability value. So, or its probability value is higher than the significance value. Okay, I hope that's clear. Critical value is how far it is from the mean or the center. Okay? How far critical value. So we can test our hypothesis based on critical value, or we can use the p-value instead. If it's higher, again, it's somewhere in between or it's within our acceptance region. If it's lower, then it's outside the acceptance region. So meaning it's in the rejection or critical region. The shaded portions, the color blue. Okay. So again, if our statistic falls in these regions, we reject null hypothesis. Okay, so rejection region, the range of values for the test statistic that leads to the rejection of the null hypothesis. And in a two-tailed test, these are located outside. Okay, but if it's a one-tailed test, then we only have one tail. So it's either on the leftmost part of the curve or on the rightmost part of the curve. Okay, and the rejection region should cover a probability of significance level. Okay, so whatever the area under this portion and this portion, that constitutes your significance level. So when we say 5% confidence significance level, then actually for the entire curve, 5% of which is covered by your rejection region. Okay? And 95% is covered by your acceptance region. Okay? And I mentioned the term critical values or critical scores. They are basically the same or synonymous. These are specific values in the distribution of a test statistic that define the boundaries between the acceptance region and the rejection region. Okay? So boundaries are the limits. Okay? Critical values. Right. So talking about one-tailed and two-tailed, again, I mentioned already, if it's our hypothesis has something like less than or greater than, then it's a one-tailed test. So either a left-tailed or a right-tailed. Okay. Um, left-tailed if the mu is our null hypothesis says the mean is greater or equal than the actual value. Okay. Right-tailed if we are claiming our null hypothesis is claiming that the the mean is less than or equal than the actual value. Okay. While the two-tailed test again, null equal, alternative not equal. Okay, so this is the illustration of the one-tailed test and the two-tailed test. All right. So they all have both acceptance and critical regions. Okay, I hope we you got it. Right. Now, speaking of the when it comes to estimation, we have to take note that our statistical test might commit some types of error, right? Like false positive or the type 1 error and the false negative or the type 2 error. Um, Type 1 error occurs when the null hypothesis is rejected even though it is true. So, to prevent that, a lower significant level is reduced. Okay, or the lower significant level will reduce the risk of committing such error. However, if we do that, it will increase the risk of committing the type 2 error. So you just have to choose which one do you want to avoid, the type 1 or the type 2. Okay? If you want to avoid both, then you have to be somewhere in the middle. That's why you have to choose the confidence interval or the right confidence interval or significance level. So, um, okay, you can take a screenshot of that or you can observe or you can pause the video if you want. Okay, so I will not discuss anything here. We have a better illustration in the next slide. Okay, so take a screenshot, please. Three, two, one. Okay, next. So we can understand more about those things that we mentioned by first um uh we're going to have a more specific uh example. Okay. So first, in terms of z-test, we have these things. Z-test is used to determine whether the sample mean is significantly different from a known population mean when the population standard deviation is known. And we usually based on the z-score, are also known as the standard score. It is a measure of how many um, standard deviations an individual data point or observation is away from the mean of a distribution. So if this is the mean, okay, the center is the mean, then the farther it is from the center, the higher the z-score. Okay? Or in other words, the higher the z-score, the farther it is from the mean, which means the closer it is to the left tail or the right tail. Okay? The closer they are from being rejected to being rejected. Um, what else? If the standard deviation is known, we use this formula. Okay, just divide by S. But if we don't have the S, then we use the population standard deviation divide by the square root of n, or the sample size. Okay, remember S is the sample standard deviation, while the what letter that, I guess that's sigma. The this one, rho or phi. I think it's phi. The Greek letter phi. Um, that's the population standard deviation. So you have to divide it by the square root of n. Okay, that's for one tailed. I mean for one sample tests. If we have two sample tests, then one of the equations that we can use is this one. Okay, so we A represents the ones that for sample or group A, while all the B's refer to the ones for sample B or group B. Okay, so I think we have some sample problems in our handout. Okay, and usually in Z tests we use a Z distribution table, right? So this is just to um we're not going to discuss everything here, how to use it, because it is long story. And usually what we want is to we normally use just one specific confidence level, and I will tell you in a while. Okay. Anyway, this slide only shows how the three most common z-scores were derived, okay, from our confidence levels. Okay, so we can skip this part. All right. I think I have to go back this part. Huh? Right. I guess this one. Or anyway, I just show you the sample problems in the handout. All right. See, I'm looking for the part where we have our three most common z-scores. Okay. Here we have, okay, we just have one example. I think it's enough. Just remember the most commonly used confidence level is 95%, corresponding to 5% significance value. Okay? Why this is the most common? Because we want to avoid both type 1 and type 2. We want to meet if 90% is if 90 and 99 both have the higher tendency to commit one of the two errors, then 95% is somewhere in between them. Okay? So it's lower, it has the lower chance to commit both type 1 and type 2. Okay? So we use 95% confidence level, which corresponds to the 1.96 z-score. Okay? This is derived from the z distribution table is in this one. Okay? So now, for t-test, okay, by the way, we can skip that part because we have the discussion on our sample problems in our handout and in our face-to-face class. Okay, so you can see our sample problems in our handout. Okay. In the meantime, we try to understand what is t-test. Okay. It says here it is used to determine whether there is a significant difference between the means of two groups or to compare the mean of a sample to a known population mean. So the first one that just like z-test is basically like z-test. So when we what we are telling here between the means of two groups, that's a two sample test, while comparing the mean to a known population mean or to an accepted population mean, that is a one sample test. Okay? In this case, one sample t-test. All right. So if z distribution already has, or we use distribution if we have a normal distribution, or I mean, if we use z-test to if we are assuming if we have a normal distribution, okay, if we already have, that's why z-test. But if we are just assuming a normal distribution because we have a lower sample size, then we use t-test. Okay, we are just assuming, right? And okay. So we just make sure that the sample size is large enough for the CLT or central limit theorem to apply. And take note, the confidence intervals are often used to estimate the difference between the means of the two groups or the mean of a sample. Okay? Um, one one main comparison between the two is in terms of convenience. Okay? Both of them they have similar descriptions, but both of them are used to compare two things or compare one thing to a standard thing. Okay? But um z-test is generally easier. Okay? Beginner friendly. While t-test is quite complicated. And one of the things that make it complicated is that the introduction of the term degrees of freedom. Okay, which is a concept used in calculating the t statistic and determining the critical values from the t distribution. It affects the shape and spread of the t distribution because the degrees of freedom is just the sample size minus one. Okay, and for each degree of freedom, we have a certain t-score or set of t-scores. Okay, the t-score depends on the degrees of freedom, meaning it depends on the sample size. Where in the z-test, we are not concerned of the sample size anymore. Okay, so here sample size is a big concern. So now we I guess we mentioned this already. We can do a one sample test by comparing the sample taken from the population to the large population. Okay? Meaning we are comparing our um the mean of for this and our mean for the sample. We are testing if whether there is a significant difference or not. None. Okay? But if we do two sample tests, then we have two samples. We are comparing them. Now, this is what I want to introduce here. We have the paired sample t-test. So this one, we have the same sample, but we are comparing them in two different scenarios, like two different times. Okay? So for example, we use this for pre-test and post-test. Like before the training, we have our respondents take the test. Okay, we record their scores. Okay, now after the training, the same respondents, exactly the same respondents, will take the same test. And then we are going to compare whether there is a significant difference between their before training and after training results. Okay, so that's an example of paired sample t-test. We are comparing two scenarios for the same sample or the same group. Okay, so now we have the formula for this. Okay, you can observe them. One sample test, you just need the sample mean and the population mean divided by the sample standard deviation and the square root of the sample size. But if we do the two sample test, we use this formula. All the number one refer to the first sample or the first group, while all items numbered two refer to the second sample or the second group. But as you can see in the paired t-test, we just need the mean of the difference between the paired observation. The difference between of uh the scores of um respondent one, for example, the before and after of his score, we take the difference. And then same respondent two, difference between the scores. Next, respondent three, and so on. Once you get all the differences, you take the mean of that and you just substitute it here, divide by the standard deviation, and done. Right? Standard deviation of the differences. Okay, so once you have taken the differences for each respondent, then you take the mean and the standard deviation of that, and then just use them in this formula. Okay, so that's paired sample t-test. Right, and these are some of the most commonly used in basic engineering research. Okay, but normally the more common is the ANOVA and the regression. Okay, so we're going to talk more about them in module 4, 3, and 4. Okay, so in the same way, t-test is also using a t-distribution table. I forgot to mention earlier, the values in this table is derived using calculus. Okay, so if you can use if you want to do the exact method, then you perform calculus. Okay, so integral calculus to be more exact. It's basically based on the principle of areas under a curve. Uh, Okay, so that's a long story, and we cannot discuss that here. Okay, so as you can see in this table, just unlike in the Z distribution table, the T distribution table has a column for the degrees of freedom because the values differ depending on the sample size. Okay. Lastly, we have the ANOVA and the chi-square. So ANOVA test if at least one group mean differs from the others. Those others could be two or more. Okay. So basically when we perform ANOVA, we have the F distribution table. So you have to get a copy of that, learn how to use it, and then you create this ANOVA test table wherein we solve for the SSB, SSE, SST, MSB, and MSE to come up with our F value. So the F value, we will just check if it falls within our acceptance range. But if not, then we reject the null hypothesis. Okay? It if we reject the null hypothesis, it means um there's one that differs from the rest. Okay? So chi-square, on the other hand, is to test if there's a significant association between two categorical variables. I already mentioned that. For example, here we have two groups. So first categorical variable is the group, okay, group 1 and group 2. So you want to see if there's association, like If you are in the group one, most likely you get to pass. While if you are in the group two, most likely you get to fail. So that's an example. We want to prove that whether that's the grouping matters. Okay? The grouping is a significant factor in whether the member gets passed or gets to fail. Okay, so we basically create an observed results table and an expected results table to get the what we call the chi-square value. Okay, or that's our test statistic. So once you have your observed and expected table, you basically plot them here. Okay, and same thing. If it falls within the acceptance region, then you accept it. But it is beyond the it is outside the two critical values, then you reject the null hypothesis. Now, I forgot to mention critical values. Where do we get them? From the distribution table. So Z, T, F, and X have their own distribution tables. Okay, z-test, t-test, ANOVA, and chi-square, they have their own distribution tables. So that's where we derive our critical values. But then again, in by default, we we can use Excel to derive the automatically derive the critical values. Okay. But in the meantime, we are going to discuss how do we perform this statistical test in our face-to-face discussion, or you can simply observe our sample problems in our handouts. Okay. So that's all for now for the concepts. I hope you have learned something. Okay. So see you in the next module. Bye bye.